invested for a big visionary, and about 14 years ago investing in this shake table, which is state-of-the-art facility. It's about 14 years old, but has been doing quite a lot of work for us. And this year we got about $160,000 to operate the control system. The table then cost us about $1 million all up. It's 6 times capable of handling specimens up to 10 tons in weight. And it can also produce frequencies from very low to very high. And all the earthquakes that can happen, we can actually cater for them. At this point, I'd like to acknowledge my colleague, Dr. Jensen Lee, who is here. If you don't want to maybe come here, so everyone would meet you and know you. The reason is that he joined us to actually get the table and get everything organized, and we'll be also running the shake table today. So thanks, Jensen. This particular work with mud started some 5-6 years ago when I got an email suddenly among so many emails we get from one of our students who was in El Salvador at the time, Dominic Dowling, who is also here. And he simply sent a 2-liner saying, I'm in El Salvador, I've just witnessed the devastation of the earthquakes in that country in early 2000, and I've seen the damages that have been sustained by mud brick houses and mud structures. And I would like to do a project in this. Is there anyone out there that can supervise or make it happen? It was one of those emails that in a bad day, in a bad mood, you would have pressed the delete button, never to be heard again. But I'm very happy that I was not in that mood. And I responded back to Dom and saying, when you come back, we can discuss it. So Dom came back and started a 1-year undergraduate capstone project that all our students have to do, and that led to a bit of sort of pushing and enticing him to a PhD, and he just finished his PhD about a year ago, and been going back to El Salvador, also to Pakistan and India to implement. That was the interest in mud structures. Of course, the system that Tom came with was not this system. It was basically a mud brick system. He actually manufactured all the bricks himself, brought it in, made them. So, which are a couple of models on my right. If you have time, maybe afterwards you can have a look. We just experimented with 11 U-shaped, similar to this, and a full house. And Dom's work, of course, as some of you may know, got some international exposure as well as national exposure. It has been on Catalyst program and also New Inventors program. Maybe at this stage to see the actual man, Dom doesn't mind to come and maybe say a couple of words about his own experiences, maybe as one of our graduates.
Well, I guess welcome everybody. It's great for all of us to be here. I'd just like to throw my support behind the work that's been done, because in this issue of providing safe housing around the world, there isn't a single solution. Solutions need to be tailored to the context and the location. So here we have a particular solution which Peter's going to talk a little bit more about. And I think the important thing is we need to be considering how we as people, as engineers, as technicians, as builders, as interested people, take the steps to support this sort of work. So I'd like to acknowledge the efforts of Peter as well as Disco and Luke in getting us to this point. And of course, none of this could be possible without the support of the university. So I'm always delighted when there's more earth being tested. So thanks. Yep.
With that introduction, later on, always students are the main force. I had a contact by 2 very keen students, Luke and Jim Michel, who are here, will also speak a few words. They actually came and said they have talked to an earth builder whose name is Peter Hickson. I remembered a name, but I could not put my finger on it until I realized that I actually had met Peter when he and Dom made wonderful sort of demo at the Powerhouse Museum that was on display for some time. And half of it was mud brick and half of it was not. And Peter had basically had the same vision of building safe houses in places where earthquakes are relevant. That was the motivation, and he had experimented some in Philippines with a system which is called top system. I think at this point, I think it's best if I let the person who came up with the idea do the talking and have a presentation. So it's my pleasure to introduce Mr. Peter Ibsen.
Okay, thanks. Bamboo Clubhouse is a contemporary sustainable approach to aid. We don't have to go over with bucket loads of money and give people all the materials and all the expertise. With this system, we can go and educate them how to use their own materials that they have at hand. A lot of people in the area where I was working are subsistence farmers or subsistence fishermen. And those people will have always built their own houses and they'll continue to build their own houses. So the system can help them, but it also can help people who have moved into town and got a job, they're professionals on the other. They've got a bit of money, a block of land, and they can pay someone who's trained to build for them. So I'd like to train tradesmen, but also show people how to build their own houses. And by doing that, they maintain the self-reliance of the local community. They're using local indigenous materials. This would have a nipper roof, a nipper palm thatch roof. The timber's locally sustainable, and earth and bamboo are available on site. They're very resourceful people, but it improves that resourcefulness by adding cob and bamboo reinforced cob to their palette of materials that they've got to use. The system had to be practical. You won't get a system adopted by people unless it's practical. The problem I had trying to introduce mud bricks into Ingorog was that the bricks weren't drying. They were just sitting in one place, drying fungus out of them. Huge mushrooms were growing out of them, but they weren't drying out at all. And to make bricks and not lose them in a wet climate like that, rainfall every day perhaps, for days on end sometimes, I thought I needed a system where I could put the roof up first and then build the earth into the structure with the roof up. That suits their lifestyle. They could put this post-beam frame up and slowly mud up the base of the structure in time, and then it dries in the structure while they're living upstairs and around the building. I also am a firm believer in appropriate technology. So this, the design is a climate responsive design. This building here is designed for tropical climate. If I was coming up with something for arid inland Australia, it would be totally different shape to that. This is a tropical design, climate responsive. I studied a book, I knew nothing about tropical design. I studied a book put out by a Swiss development agency and learned how to do tropical design with thermal mass in it. It's sort of a vernacular design. I've seen similar sort of style building in the Philippines. And some of the early colonial Spanish places were heavy based and lightweight at the top. Not this shape necessarily, but heavy downstairs, light at the top, which is good in the earthquake area. So that's the house there that I built. It was built as a volunteer house for Australian business volunteers. Here's one of my colleagues over here, Peter Richardson, who has spent time in the house with me. There's another volunteer over there, an accountant. So I think he appreciates that the house worked okay. feet. It was better than the concrete and iron building next door. It was sort of nice and cool. Now, you can imagine you see the dormer window jutting out the front. If you cut the building down the right-hand side of the building from the front door, what you've got here, replicated here. This is a half scale of what's in that photo there. See the nipper thatch, well, shade cloth is the closest thing I can get in Sydney, nipper thatch, unfortunately. So, this is the cross section of the building. I'm looking into the living room there downstairs, and upstairs there are 2 bedrooms. You see 2 bedroom doors into those loft bedrooms. It's actually a 4-bedroom house with a sleeping loft, so it's almost 5-bedroom house, which is very luxurious over there. But downstairs, in actual fact, is the size of a single car garage in Australia, about 6x3. That's a view looking into this. Okay, so Bamboo Pop House addresses the housing needs of the Philippines because it provides safe, healthy, comfortable, affordable, durable and desirable housing. It's got a bamboo pole with a structural diaphragm, so it's got ancient technology, but it's also got engineering principles put into it. Structural diaphragm and reinforcing. Safety is yet to be tested. We're here for that. But the healthy, it's got natural materials. You come in the front door and you go up into the landing, there'll be a compost toilet, dry compost toilet in this house in the Philippines. The problem in the Philippines is that high rainfall, very small blocks of land, probably 70 square metre block of land, which is tiny. It's unbelievably tiny. But it's like a caravan park, I guess. A lot of caravan park, and the house is like the size of a caravan annex. But they have a septic tank there, and they have groundwater as well for drinking water. And the cross-contamination, the rainy season is horrendous. So I've put in a dry compost toilet. I've also put in a simple grey water treatment system so that the water can go straight through sand gravel filter and out onto the vegetables. So it's got that in there. So it's comfortable because it's climate responsive. It's affordable. This house is probably getting towards luxury really, but it wasn't a really cheap house. The price was cheap, but the house was high quality. Durable. We added local materials, rice hull ash, to the earth to make it less prone to erosion because of the high rainfall and the driving rain and so forth. We also used the slab differently to the way they were using it before, so it was locking out termites. It's worked safely. It's desirable, it's attractive, it's sort of an immaculate design. It has a veranda on it, which is integral in a Philippine house. It's very spacious. And we've also, the guys I trained have been contracted to build several more houses in that area, so it's been taken up mainly by expats from Australians over there. The house over there costs 200,000 peso, which is 5,000 Australian dollars, which is a little bit expensive for a low-cost house. Probably try and do it for half that amount. But this house had double the Mackin wall, so split bamboo on both sides of every wall in the house, which is luxury. They usually have one side done. Usually they don't have any painting done. Usually they don't have hot and cold running water, or 2 double power points in every bedroom, or lighting, and a lot of things that we had in that building aren't normally in there. We had a full kitchen with gas, fridge, electricity, so I think it was good value for money. And that included landscaping as well, so it's fully finished. So it's very robust. In a heavy wind like a monsoon, the roof structure is embedded by the post and beam structure into the earth wall, so the whole thing is not lightweight, can't blow away. It's sort of got that weight on it. So it should be fairly durable. And we've locked out the termite with the slab. The design won first prize at Grex 07 Sustainable Expo last year. So how does the system work? In this particular house, I started with a concrete slab with edge beam, posting beam frame for the first floor on the attic roof. Went up first, put the roof on, and then you can work in the underneath out of the sun, out of the rain. Vertical bamboo reinforcing is fixed to the slab and then first to the first floor, and that runs. There's a post at this very end where the door will be fixed in normally. There's a post in the corner where it returns around the corner, and each side of the window there's a 1-inch bamboo pole reinforcing that wall. And the cob is just the earth mixed with straw, melded into the wall, like mud welding around the bamboo frame. That's the slab. Needs to invest in durability. It's a barrier to termites the way we've done it. But it's minimal size because it's a 2-storey house, so it suits the very small block frame. It minimises that cost of the concrete slab. Here's that's the frame in reality over there. I only had 3 weeks to do it, so I've actually started the top before the roof was on. Normally I'd like to do that. The attic frames are extremely strong. They're triangles, but they're very good use of space. The materials, huge use of space. You can see the bamboo up the side of that window, and there's a little metal connection we've used to join it between. So this is Marv and Gabby in the Philippines mixing cob. Cob material is just a subsoil, so you not the topsoil, the very organic topsoil, not the heavy clay, material in between which has a mixture of clay, silt, sand and maybe some small gravels. So the clay is the cement, it's the binder. The sand, the silt, the gravel, the fillers, and the straw is added, and that's like a reinforcing. Allows you to build in a monolithic wall in a slab-like structure and control the cracking. The vertical bamboo, but also the horizontal bamboos that we've made out of split bamboo has been made into like a ladder mesh, and that's built into the wall. In reality, every 400 millimetres this far, so there's probably 5 or 6 to the top, runs right through. In the model it was every 200, and you can see the first 2 layers here sticking out of the wall. So that's where I had to leave the project and come home, and the guys finished it by themselves. You can see that window downstairs is made up of bamboo ladder lintel, just to show them how I wanted to do the same system. So the advantage of the bamboo cob system is that the walling is one monolithic structure. It seems to behave differently to mud brick, which is made up of modular pieces. This behaves in a very monolithic fashion. Now the composite of the bamboo and the cob are like reinforced concrete. Bamboo is like the steel, the cob is like the concrete itself. The bamboo is good tensile sort of strength, and the cob has good compressive strength, so they're acting together in a composite way. The vertical bamboos are connected to the structural diaphragm. Now, I wanted to get a meaningful structural diaphragm in the building. Now, if you do a drawing and say put in a structural diaphragm, which is a strengthening plane, a plane of strength, like a plywood ceiling or something like that. If you put on the plans that you want one, and they can't afford one, they won't put it in. But if it's a floor, they have to put it in to use upstairs, so it's a meaningful structural diaphragm. Can't be left out. So this cable will be working in this direction. The walls in this direction are in plane, so they'll be trying to rack, and the back wall is the outer plane wall. It'll be trying to resist bending and flopping and moving like that. It's all tied into that plane of strength, structural diaphragm. So hopefully that won't happen. It won't be allowed to happen. So the weight of the knob, as I said before, resists the uplift on the building long wings. So we've got the strength of reinforced concrete, the durability of that, but it is sustainable and it's affordable as well. So what I'd like to do is to get back overseas and implement this through training and have a small village built. A small village is a display of this sort of thing. It's a training centre and get some trainers, local trainers trained up so that they can take it further and spread it through the Philippines or Indonesia or wherever. Probably need to publish a banded training manual in graphical form. The language is not so much a barrier. And I'd like to do future testing of mud brick to make it stronger. The Australian earth building industry is professional. A lot of earth building around the world is not professional. There are mud artisans in Egypt and in the Middle East and all around the world who are extremely professional and who can build a 20-metre dome. They know how to do it, but self-builders around the world often do a fairly shoddy job of it. It gives earth building a bad name. Earth building in Australia is very professional, and earth building in Australia has a lot to offer overseas earth builders.
Yeah, so first of all, thanks for coming everyone. As Peter was saying, the material itself is just basically a mixture of sand and clay, 50% sandy soil and 50% clayey soil. And one of the important things is to get the mix as right as possible. It's all done qualitatively just by seeing how much clay you can get in there to hold the straw into the mix as you're going along building it. But at the same time, too much clay will also mean you have shrinkage cracking as the structure starts to dry out. So it's important to get that mix right. So once we mixed up our soil mixes in water in wheelbarrows, we pour them into the ground onto this mixing mat, which you can see, and pouring straw into it. We just basically mix the straw in by foot, and it's a very, very physical process. I can tell you, I'd say it's almost equal to running a marathon, and as you mix the straw in by foot, it takes a long time. Once the mixes are ready, we build our bamboo reinforcement system. The vertical poles go in first, and I guess the best way to describe the material once it's mixed is like Play-Doh. You just basically build it up in blobs and mold the wall just by eye, really, or qualitatively.
Our involvement in this was more for our graduate thesis project. We had slightly different objectives to what Peter's done. This house that you see here is really more Peter's baby. We built two other samples over there, but this has its own merit. We're testing the value of the structural diaphragm and the effect of the windows, if any. We had three main objectives, which was to see whether compare cob to mud brick, to see what value the structural reinforcing had, and to see whether or not a house made out of cob will sustain an earthquake. So this is the method that we used originally, our hold downs. There's a different method of hold downs used here, which we think might be a little bit more appropriate. But our design was based predominantly so that we could compare against Dr. Dowling's research. He did extensive research for over 3 years. He built 11 U-shapes and a full house. We obviously didn't have the time available to do anything near that, but we did build two. We also try to maintain as much other consistency with the results as possible. We used the El Salvador January 13, 2001 earthquake, which is a magnitude 7.7 from memory. The acceleration's in centimetres per second, but I understand it's about 2.5 Gs is the force that the house was, which was exerted to it. So we've used the recordings which have been taken from the site in El Salvador, but they have been modified slightly. There's the table will only go up to a certain frequency, and that frequency isn't significant. The house won't fail at that frequency, but there are a few modifications just to make the test a little bit more valid. But we've used the same testing for both. So what we've done is we've used a testing hammer that you can see there, and we've used the inputs. You can see the hammer's wired and there's accelerometers, and that's fed into the computer. When we hit the wall, we can know what the frequency of the building will fail at, what its weakest frequency is. So we've then scaled our inputs to match that. So to take into account, in effect, that this is a half-size house, we need an earthquake that accounts for that. So you can see that the dark blue is what the real earthquake, as recorded in El Salvador, was. The light blue has been shortened, has been scaled to make it as severe as possible. If we give it an unscaled earthquake, that house will stand there regardless. By scaling it, we have a much better chance of getting a realistic result. I should point out that the earthquake in El Salvador was incredibly devastating. I believe 157,000 houses were destroyed. I have no idea of the human toll, but I know that of those, it also is very relevant to earth building. Of those 157,000, 113,000 of those houses were earth houses. So that's why we agree with Dom's choice, that I think it's an excellent choice for an earthquake, because it's known to damage mud brick houses. Again, you can see the hold down situation. We have to, because we've only got half a house here, we have to somehow duplicate the other half of the house. It's not practical for us to build a full house on that table. Instead, we have to allow for the restraint that would have otherwise been applied. The choice of the U-shape also focuses all the attention in the outer plane wall and in the corners, which Dom's research has shown that that's the key method of failure for mud brick houses. In terms of severity, rather than just giving it a pass-fail, we've taken the severity, so that's measured in displacement in millimetres or in acceleration in millimetres per second, and rather than just saying yes, it's past the earthquake, we've started off at gone incrementally from 25%, 50%, 75%, 100%. That's then repeated to then show the effect of subsequent earthquakes. Now, Dr. Dowling's research is based on retrofitting mud brick houses that already exist. These houses are there and something needs to be done to make them safe. So he came up with 11 different permutations to test which of these would be the safest. Ultimately, he was able to produce a reinforcing condition that would withstand the earthquake. However, none of these retrofit solutions were able to withstand a second pass at 100%. They were able to withstand one earthquake, but a second earthquake was unlikely. The difference with we have two reinforcing conditions. We had one cob structure with just corner posts and one without. The one with corner posts withstood the full simulation without any cracking, as did the one with bamboo reinforcing. We were able to fail it by producing a sine sweep, but that's really not representative of an earthquake. So I think without any further ado, I think we should get to testing and see if this one will withstand the same. This is
Yeah, I don't.
Okay. Keep us down and start. Okay, stop. so it's safe to get on the table.
Oh, okay.
And there's a cracking already next to the window, if you see it. Just the cracking, just
Was that at 50%?
125%.
Ooh, okay.
It's already exceeded what the original earthquake was.
Yeah.
So this is very strong.
Wow.
If the Dom's model before 100 will crack it. Yeah, so this.
And
is
it's
much
cracked
stronger.
now,
Yeah.
but yeah.
That's it. Did you see any more mistake in the first offshock?
What did you do?
What I did is I started wrong. I realized I didn't put the hydraulic power on. Well, quickly put the hydraulic power on, but it's already the program already halfway.
But why missed the start of it? Because of
Doesn't matter,
No,
have a
that's
second.
not important. The second one is more important.
I've actually missed the last